Hello, I'm Jack Forbes, and today I'm going to be going over control systems. I'm going to start with the wireless connection from the driver station laptop to the robot. So the drivers control the robot through a joystick, which is connected to the driver station laptop. The driver station laptop is connected to the robot through Wi-Fi, and that Wi-Fi network is being hosted on the radio on the robot. This allows for the driver station laptop to communicate signals to the robot and for the robot to give data back to the driver station like its current battery, the position of its motors, and other related information. The radio is connected to the RoboRio, which is the computer that controls the robot. It controls all the motor controllers, takes in any inputs, runs all of our code. It's the brains of the operation. It's connected via an Ethernet cable. This Ethernet cable can either transmit data or power and data, called PoE, or Power over Ethernet. Usually we run PoE because it's one less wire to run, one less wire that can fail when we're in a competition, and it just simplifies wiring. So we would go from the VRM, which is the voltage regulator, which outputs a 5 volt, 12 volt 2 amp signal. Then that would go into a PoE injector, which puts the power into the Ethernet cable and then to the radio. The other side of that injector would be connected to the RoboRio for data. If we ever lost power, it takes 40 seconds for the radio to restart, and we'd be out of the game for that period of time. And it happened again, another 40 seconds. CAN is the main way that the RoboRio controls all the other motor controllers, PDP, and gets data from the robot. It's the main way that we communicate locally on the robot. It was originally developed for use in cars and still is in pretty much every single modern car today. It can be daisy chained, which means you can go from one device and then say you go from your motor controller, daisy chain it to another controller, daisy chain it to another. You don't have to run individual wires. You can just connect them all into a big chain. Really simplifies wiring. Every single device has a CAN ID. Every single device can be individually controlled, and they can all send data back. And we only have to use one wire going throughout the robot to do that. Really simplifies wiring. Yellow and green cannot be mixed up. You gotta put yellow and yellow, green and green, or it will not work. PWM is the other way we can control motor controllers on the robot. It stands for pulse width modulation, and it's just turning on and off a signal very quickly to encode data. It's one directional, which means you can only send data to controllers, can't get anything back. It requires an independent wire for every single motor controller, and it requires an individual port on the RoboRio for every single motor controller, which means you are sort of limited by how many DIO ports you have. Servo PWM is another way to encode data. It looks like this. It's the way that we can control servo motors. It's just a standard. No, it looks funky, but it can be done either by a DIO or a PWM port. It is much simpler than CAN bus, but again, it cannot be daisy chained and requires independent wires. DIO stands for digital input output. We can use these ports to either input in digital signals or output them. So we can use the output function to output a PWM signal, say to a servo, or to dim some lights by flashing them quickly with a duty cycle of a certain %, which would approximate an output voltage of the average voltage there. Or we can use it to communicate with servos via PWM signals. We can also use the input to get inputs from limit switches. So say we have an arm on the robot, we want to stop at a certain point, can put a limit switch on it, and when that switch is pressed down, it will read that the circuit has closed, and then the RoboRio can run some code or tell our code that's running on it, hey, the switch is closed, you want to stop that motor now. That's really useful when it comes to having arms on the robot or any other part that cannot go past a certain limit. Analog in is similar to DIO, except we can read thousands of different discrete values, 4095 to be exact. This allows us to, say, put a potentiometer on a motor arm or an arm on the robot, and get close to the exact position and send that back to the RoboRio where we can use it in code. This is useful if we need to know where a part of the robot is or to know how far a certain part has spun. The RSL, or robot signal light, is a crucial piece of safety equipment. It indicates if the robot is on, off, or enabled. If the robot is off and has no power, the RSL is going to be off. If the robot is plugged in but disabled, RSL is going to be solid orange. And if the robot is plugged in and enabled, it's going to be blinking orange. This is crucial because if you don't know if the robot's enabled or not, and you stick your hand or head into somewhere where the robot's about to move, you can get injured, or the robot could, you don't see it coming, run you over. Obviously bad things, and the reason we have the RSL, the reason it's a mandatory piece of equipment on every single robot in a visible place, is so people around the robot know if they can get close to it, if it's safe to do so. And here are some pictures of last year's robot. We can see the RoboRio and that clear case on the side, and the PDP sort of hidden inside the robot. The CAN bus would be going through all the motor controllers and to any other sensors we have. Just a good way to see how this all integrates into an actual robot.